Okay, so this chapter is about the simple harmonic motion. We will define simple harmonic motion. But before starting to defining the simple harmonic motion, we should first learn periodic motion. What is periodic motion? If an object, if a body repeats its motion about a path or about a circle, so then we say it is a periodic motion. And repeated motion of a body is called periodic motion. And an object can repeat its motion by two ways. One of them is the object may repeat its motion over a closed path, like Earth orbiting the Sun or planets orbiting the stars. So this is a kind of periodic motion. And second one, the object can move over the same path back and forth, repeat its motion by this way, like acrobat swinging on a trapeze or swinging clock of a pendulum of a clock like this, or a child on a playground swinging back and one over the same path. So these are periodic motions. And as I said, one of them is on a closed path, the other one is on a line path. Over the same path, object goes back and forth. Both are called periodic motion. The basic idea for periodic motion, motion must repeat itself, so this is called periodic motion. And the motion of a mass attached to a spring is the simplest type of periodic motion. So this is a string, and then if you see that an object is attached to a spring and it is going back and forth or on a over a same path. So this is a simplest types of periodic motion, and we will study this in this section. And of course, to understand the characteristic of this motion, first we should understand how spring behaves at some circumstances. So then we should learn about the spring first. So if an object is attached to the spring, as you see here, if you stretch the spring or if you compress the spring, so this is unstretched position. Here it is stretched, here it is compressed. So spring starts moving back and forth around this unstretched position. So that's why we should first understand how we stretch a spring or how we compress a spring. So we will now study the behavior of the spring when it is stretched, when it is compressed. And if we stretch a spring or compress a spring, so one thing is clear that, for example, here is a spring attached to different masses. Initially a mass, it is initially the unstretched position here. Later a mass is attached to the spring. Spring is stretched some distance x. But if you double the mass, you are going to observe that the amount of stretch is doubling. In fact, these masses are applying forces on the spring because gravitational force is acting on the spring, and this gravitational force of the object is stretching the spring, which means as force increases, the amount of stretch also increases. However, when the ratio of force and the stretching is constant, here is F and X, so later 2F and 2X, and after that 3F and 3X. When we divided force by distance or amount of stretching, so we get a constant number. This constant number, F over X, is defining a property of the spring, the ratio of force divided by stretching, force divided by compression, defines a property of that spring, and that property is known as the spring constant and represented by K. This spring constant is a number uh, calculated by F over X. As I said, K is the symbol of spring constant. Its unit is Newton per meter, or Newton divided by meter. If we cross product it, we can get the force is equal to K times X. And this spring constant measures the stiffness. Stiffness means how hard or how tough a spring is. Stiffness measures the stiffness of a spring. It's a positive number, so like 100, like 10, like 1000. So as stiffness increases, this number will increase. Or less stiff spring will have a smaller K. but it's always a positive number. A greater value of K means it is a stiffer spring. A greater force, if it is a stiffer spring, which means a greater force must be applied to stretch or compress a stiffer spring. As you see, here are different springs. So each spring will have a different spring constant. So that's why spring constant determines the how hard or tough spring is, how easy or difficult to stretch or compress a spring. And uh, there is some questions in your book. I will just show one of them, which is the sample problem. As I said, this is unstretched spring, but if a mass of 0.55 kilogram attached to a vertical spring, this is the vertical spring, and this spring stretches the spring by 2 centimeters. So initially unstretched, later you suspended 0.55 kilogram, so it's stretched by a distance of 0.02 meters, which is 2 centimeters. From its original equilibrium position, original unstretched position is this. What is the spring constant? So to calculate the spring constant, we need force divided by x. We know what x is, which is 0.02, but what force causes this spring to be stretched? Of course, it is the gravitational force acting on the spring. We calculate the gravitational force by mass times free fall acceleration. A mass is equal to 0.55 kilogram. G is 9.81. If we multiply this two, we will get 5.4 Newton, which is this force is stretching the spring. And after that, right here, 5.4 Newton. Stretching is 0.02. So when we divide them, we got spring constant of this spring. So this spring will have always that constant. So this constant belongs to that spring. And every spring will have a specific spring constant. Another spring will have another spring constant. So it depends on the length, depends on the thickness, that constant is changing. And then now we will define now simple harmonic motion. This is how stretching or compression related with the force and related with decay. We got this, but now we will study this back and forth motion of spring and objects attached to a spring. If a mass is attached to an unstretched spring, it is unstretched initially, so this is the mass. Assume that this mass and this spring is in a medium which has no free of friction. There is no friction. So if you stretch a spring by applying some force, of course, to stretch a spring, you should pull it. When you pull this string, it's going, of course, there will be some stretching. So this stretching is represented by X. If some force is applied on a spring, which is, I said, this force is F applied, the spring stretches by X. And we can calculate how much force is required to stretch the spring if we know what K is. So that force is going to be K times X. So if you apply more force, so you will see that string is stretched more. So as applied force increases, displacement. That is called displacement. Uh, because according to initial position, it is stretched and this object is displacing. This object is moving from here to there. Displacement of this object. So displacement x is proportional to x. Pardon, if force applied, displacement is proportionally increases. So more force, more displacement. Much more force, much more displacement. They are directly proportional. In fact, it is about this force. I'm that one. Here it was vertical, but here it is horizontal. But later, and when you are pulling this force, you are going to feel that some other force is pulling the object back. So this force is applied by the spring. As you pull the object to the right, spring is pulling the object back to unstretched position to the left. So if applied stretches the spring pulls the mass or object back by exerting an oppositely directed force, which is named as elastic force or spring force towards the unstretched position. So this force is in the opposite direction of the displacement. Yes, displacement is to the right, but elastic force and or another name is spring force, is to the left. For that reason, in their equations, there's a negative sign. Negative, F elastic is equal to negative Kx. This negative indicates that this elastic force or spring force and displacement are opposite in directions. So they are opposite in directions. And this equation is known as Hooke's law. Hooke's law is defining. So if you stretch a spring, if a spring is stretched somehow, spring will pull object back to the unstretched position. This force is directly proportional to displacement. Yes, as x increases, this force also increases in magnitude. Directly proportional in magnitude. I mean, in their directions are opposite. It doesn't mean that they are not directly proportional. They are still directly proportional in magnitude. But as x increases, elastic force also increases in magnitude, but their directions are opposite. So this force always pushes or pulls the back of the object or mass back towards its original unstretched position. If you stretch the spring so to the right, so this force pulls back object back to the left. If you compress the spring to the left, this force will pull object back to the unstretched position again to the right. So for that reason, this object always wants to get the spring to its unstretched original position. That's why this force is sometimes and generally called as restoring force. So in a mass spring system, this elastic force, other name of spring force, is this restoring force, pulls object back or pulls the spring back to the unstretched position. Öyleyse, if it is asked you, which force is the restoring force for mass spring system, it is the elastic force or it is the spring force. What is the equation for restoring force for a mass spring system? It is negative Kx. This can be a ministry exam question. Tekrar söylüyorum. Bu önemli çünkü. So what force is the restoring force for mass spring system? So it is the elastic force or other name, spring force. How can we get the equation for this restoring force, which is negative Kx? Negative Kx is the restoring force for mass spring system. And if we release this object, I mean, of course, you are pulling with some force, applied force, a spring force or elastic force pulling the object back. As soon as applied force is removed, so this elastic force starts, object pull back to unstretched position. But when object is pulled back to unstretched position, it will not stop there because it gains some energy. It will pass this point, this unstretched position, to the left and start to compress the spring again. When it compresses the spring, this time direction of elastic force changes. It becomes like this to the right, pulls back to the unstretched position again. So that is why this object, this restoring force, will cause object to vibrate back and forth over the same path around this unstretched position like this one. So if any periodic motion that is a result of a restoring force is defined as simple harmonic motion. So this motion is known as simple harmonic motion. So maybe I can show it here. This is an example for this. Dokunamıyorum çünkü. Okay. Okay, this one, as you see, it is oscillating or vibrating around this unstretched position back and forth. So this is a simple harmonic motion. So definition of simple harmonic motion is this. It's a periodic motion. Yes, it is repeated motion, but it's a specific type of repeated motion. So what is that specific thing? So any periodic motion that is the result of a restoring force, the result of a restoring force is described as simple harmonic motion, which means there must be a restoring force. There can be different types of periodic motions, but all are not simple harmonic. Only the periodic motion, which is a result of restoring force can be defined as simple harmonic motion. And the position of the object when spring is unstretched or uncompressed is called equilibrium position. So this is the equilibrium position, and at this position, this spring is uncompressed, this spring is not unstretched. And when the spring is stretched or compressed, this spring stores energy, potential energy. This energy is known as elastic potential energy. So this is unstretched spring. So if we pull it by some distance x, so energy stored in the spring is called elastic potential energy and calculated by 1 over 2kx squared. This equation is studied in the 11th grade, but this will help us to understand or to define the simple harmonic motion, especially if it is involved with energy. So K is spring constant, which means if spring constant is great, bigger, so then elastic potential energy stored in the spring is greater. Second thing is displacement. How much you stretch a spring or compress a spring, so then energy also increases. So two things can determine the elastic potential energy. One of them is the spring constant or elasticity or stiffness. Another one is how much you stretched a spring, x, displacement of the spring from unstretched position. But it is squared. We are not going to use this squared part, but we know that if you double the stretching, elastic potential energy increases by a factor of 4 because it is squared. So no compression or no stretching, which means if x is 0, elastic potential energy is 0. So if the more the spring is stretched or compressed, the more the elastic potential energy stored in a spring. Of course, initially you should compress and stretch it by your hand. I mean, spring itself cannot compress or stretch. First, you are going to pull, you are going to apply some force, you are going to stretch the spring. After that, you will release the spring, and then spring will start moving back and forth, will start making simple harmonic motion by energy, which is given at the beginning by your pull. So if you don't pull, of course, it will not start oscillating. And this is an example in your book which is explained, bow string and arrow example. So a bow is also an elastic object. Elastic object is an object whose shape can change, but when you apply a force, shape can change. However, as soon as you release the force, it will take the original shape. This is definition of elastic object. So you are going to apply a force initially, and then you are going to change the shape of the object by applying force. As soon as you release the or remove the force, object must take its original shape. This is the definition of elasticity. So a bow is also an elastic object because when you pull the string by some force, this bow changes its shape. As soon as you release the string, so then bow takes again the original shape. So once bow's spring is pulled back, the shape of the bow changes. It is similar to pulling the spring. When you pull the spring, you are changing the shape. It's becoming longer, and you are deforming the spring. But when you release it, it takes its original shape again, elasticity. So this bow is also the same. Once the bowstring is pulled, so bowstring is attached to two ends of the bow, and then this causes shape to be changed. Of course, as shape is changed, what is stored? Elastic potential energy is stored. By changing the shape, in fact, you are storing elastic potential energy in the bow. So the energy which changes the shape of the bow is stored in the bow as elastic potential energy. Of course, then you are going to release the bow as soon as bow is released. So this, when the bowstring is released, together with the arrow, this elastic potential energy will be converted to kinetic energy. Kinetic energy of what? So, of course, arrow gains most of the elastic potential energy. Most of elastic potential energy of the bow is gained by arrow as kinetic energy. However, the remaining part, a very small part of this elastic potential energy is converted to kinetic energy of bow and bowstring. Yani this bow is still moving your hand because vibrating, string is vibrating, so they still have some kinetic energy, but not so big. But still, we can say that yes, they also vibrate for a short time. So this vibration also says that yes, they also gain some of the kinetic energy. Then kinetic energy of the bow arrow and bowstring after releasing the bow must be equal to originally stored elastic potential energy in the bow. So this is known as mechanical energy conservation. So at the beginning, when you stretch this string, when the bow stores elastic potential energy, as soon as you release the string, bow, arrow, and bowstring, this tree gains all this elastic potential energy as kinetic energy. And this is the brief explanation about the elastic potential energy in terms of arrow, bowstring, and bow. But the questions are mostly asked about the oscillating mass spring system like this. So for the oscillating mass spring systems, so then we should know 1, 2, 3, 4, and 5 quantities are changing continuously. Restoring force, acceleration, velocity, kinetic energy, and elastic potential energy. First, equation for restoring force is k times negative k times x. Negative kx. This negative sign indicates that, first, restoring force is always in the opposite direction of displacement. For example, here, displacement is in positive x direction, but restoring force is in negative x direction. Here, displacement is in negative x direction, but restoring force is in positive x direction. So first, we should know that restoring force is always in the opposite direction of displacement. Here, no displacement, no restoring force. First thing is we should know about the restoring force. As displacement increases, restoring force increases because F is equal to negative K X. Second thing is acceleration. Newton's second law, F is equal to M times A, indicates that acceleration and restoring force in the same direction, always in the same direction, and also proportional. So which means at maximum displacement, at negative x maximum, here when the object is stretches, compresses the spring to the negative x, so direction of the restoring force is in positive x, acceleration is also in positive x. So because object is compressed the most, so restoring force is maximum, acceleration is also maximum. Right here, because there is no compression or no stretching, restoring force is 0, acceleration is also 0. When the object is at positive x maximum, so because displacement is to the right, so restoring force is to the left, acceleration is to the left. Because it is stretched the most, so restoring force is maximum, acceleration is maximum, which means restoring force and acceleration proportionally and in the same direction. Proportionally changes and always in the same direction. Second thing is about the elastic potential energy. I will continue with elastic potential energy because we know that elastic potential energy is changing with x. If x is increasing, so elastic potential energy must increase. If x is 0, elastic potential energy must be 0. So in the equilibrium position, because x is 0, elastic potential energy must be 0. But when the object causes this spring to stretch the most, elastic potential energy must be maximum because maximum stretching or maximum compression, elastic potential energy must be maximum. But kinetic energy and elastic potential energy are inversely changing. they are inversely proportional. Why? Because sum of them always constant. As elastic potential energy increases, kinetic energy must decrease. When elastic potential energy is maximum, kinetic energy must be zero. Or elastic potential energy is zero, kinetic energy is maximum. Or at positive maximum stretching, so elastic potential energy is maximum, kinetic energy is zero. It is logical because this oscillating object stops here at positive maximum. If it stops, which means kinetic energy must be zero. So velocity must be zero at this maximum stretching or maximum compression. So at maximum stretching, which is at positive maximum, or maximum compression, which is at negative maximum. So velocity and kinetic energy both are going to be zero. But at equilibrium position here, so it passes with maximum kinetic energy, also it passes with maximum velocity. So at equilibrium position, the end velocity and kinetic energy will be maximum. And also because elastic potential energy is inversely changing, elastic potential energy must be zero at equilibrium position. Okay, any questions about this table would you like to ask? All right, I will continue with next slide. So in an ideal system, mechanical energy of the system keeps constant. As I said, total mechanical energy, which is sum of kinetic energy and potential energy, keeps constant. So mass spring system would oscillate indefinitely, which means infinitely. But it is ideal. What does ideal mean? Energy is not lost, no friction. But in a physical world, always there is friction, and this friction retards the motion of vibrating mass. So it's some energy will be lost as time passes. So system loses mechanical energy. If energy is lost, of course, system will oscillate back and forth with a longer amplitude. But later, this displacement will get smaller and smaller. Finally, it will stop. System eventually comes to stop. This is known as damping. So decrease in the displacement of an oscillating mass spring system as time passes because of the friction is called as damping. And this is a good movie about damping. First system is undamped, but if you put this object into liquid, because liquid exerts a greater friction or resistance, for that as a system quickly will damp. First, they will show you a system which is not which is simple harmonic motion, but later damped system. So the first one, this is simple harmonic motion, as you see, because air exerts a smaller friction force, very, very small. For that, as in this system will oscillate for a long time in air. We can neglect air resistance for air, but later, if you put this into a liquid, as you see, very quickly, oscillation stops. So this is called damping, what we are talking about. Energy of this mass spring system will be easily lost, and it's going to damp, or this sometimes called, this oscillation sometimes called damped harmonic motion. But is it written in your book? No, it's not written in your book. But damped harmonic motion. But damping is defined if a system loses energy, if oscillating vibrating system loses energy, the system mechanical energy decreases, and for that reason, at the end, system will come to rest, which is called damping. And second oscillating system, very popular in, or which is going to be studied in physics, is motion of a trapeze acrobat. So motion of a pendulum. Pendulum is an object hung from a fixed point so that it can swing freely back and forth. So the first example in giving in your book is a swinging trapeze acrobat. So if a swinging trapeze acrobat's motion is a periodic motion, we know about this because it's back and forth. But is it simple harmonic? We will try to understand it first. So swinging trapeze acrobat is a physical pendulum. First, we should know that. What does physical pendulum mean? So, first, its mass is distributed over a large area. As you see, there are two men, and then area of their area with the air is very large. So, very large area, very large volume, the mass is distributed. Second, friction and air resistance have a very important, significant effect, so they cannot be neglected. So, this energy lost here will be very very significant. You cannot say that there is no energy loss. So that's why this system will come to rest very quickly. And third one, the rope is thick. Those ropes are thick. So the mass of the must be taken into account. So you should also think about the mass of the rope, because while they are swinging, they also uses some of the rotational kinetic energy. For that reason, we'd say that such a system which whose mass is distributed on a large volume and friction of air resistance cannot be neglected for that motion, and also rope is very thick, so you should mass must be taken into account. So such a vibrating system or vibrating pendulum is known as physical pendulum. But question is this: swing of a trapeze acrobat, yeah, it's periodic motion because it is repeated motion. So if it is repeated motion, yeah, repeated. But is it simple harmonic? This motion is simple harmonic or not? We are going to now try to understand this. So it is certainly periodic motion. It's going back and forth over the same path. But simple harmonic motion is a specific type of periodic motion, because in simple harmonic motion there must be a restoring force. So we are going to search that if there is a restoring force acting on this trapeze acrobat as it is swinging back and forth. So if a restoring force acts on acrobat's motion, it should be simple harmonic. Then we are going to study simple pendulum as a model for swinging trapeze acrobat to answer this above question. So now we will define what simple pendulum is. A simple pendulum consists of a mass, which is called bob, which is attached to a fixed string of negligible mass. So as you see, this is not physical negligible mass. This bob is very small, so mass is distributed not very large area. Even air resistance and friction is neglected. So it's called a simple pendulum. So as this simple pendulum is swinging back and forth, so this is the axis of rotation. About this point, this bob is swinging. And as it's swinging back and forth, two forces acting on this pendulum's bob. One force is the tension force in the string. Second one is gravitational force. But these forces are continuously changing direction. Look at here. A gravitational force is always down, but tension is changing direction according to the position of the string. Look at here. So now, as you see, tension is shifting direction, but mg is always down to the center of the earth. And we will try to understand if there's a restoring force acting on this pendulum's bob or not. So first, we should know two things. One of them is, in mass spring system, equilibrium position was unstretched position here, and it was displacing by some distances to the right, to the left. But here in mass simple pendulum, equilibrium position is the string's position initially where it is, and displacement is measured by angle, not by distance. So that angle from this equilibrium position is representing the displacement of this simple pendulum. This position is known as equilibrium position. So at equilibrium position, angle is 0. the same as in mass spring system. At equilibrium position, x is 0. At equilibrium position, angle is 0. Then it swings very far from this equilibrium position to some angle, so it is the maximum displacement from equilibrium position. And we will now try to find if there is a restoring force acting on this pendulum's bob or not. So displacement of the pendulum's bob is measured by angle. Distance is not so much, so x is not measured, but generally theta will be used as displacement for simple pendulum. For large angles, the path followed by the pendulum bob is a curve. So it is a curve, as you see. But for that reason, for large angles, motion of the pendulum's bob is not simple harmonic. Generally, if the path of the motion gets closer to a straight line, we can say that, yeah, it is a kind of simple harmonic motion. But for large angle, it is not a straight line, it's a curved path. But if you decrease the angle, this curved line is approaching to a straight line, which means as angle decreases, path of the pendulum's bob get closer to a straight line, which means vibration of this pendulum's bob, if at small angle, is approaching to a simple harmonic motion. For that reason, they say that if this angle is less than 15 degrees, the vibration of this simple pendulum is going to be a simple simple harmonic motion. So for quite small angles, angle less than 15 degrees, so the path of the pendulum bob is almost a straight line. So for that, as in the motion of the simple pendulum is considered to be simple harmonic motion. So this is many times asked ministry exam question, so don't forget, for angles less than 15 degrees, the motion of simple pendulum is defined as simple harmonic motion. But if angle is greater than 15 degrees, so it is not simple harmonic. So it is just a periodic motion if it is greater than 15 degrees. Teacher, 15 degrees is what? As I said, it's defined in your book, less than 15. 15 is not included. And so there must be a restoring force, of course, for simple pendulum to make simple harmonic motion. This restoring force is defined as always a component of G. This pulls the object back to the equilibrium position. Look at here. Then it changes direction again back to the equilibrium position. So this Gx, X component of free fall gravitational force always pulls the object back to this equilibrium position. So Fgx, we calculate Fgx by Fg times sine theta. This Fg times sine theta is the restoring force, always pulls the pendulum's bob back to this equilibrium position. And this was the ministry exam question. So which force is the restoring force? Tension force or gravitational force? It is the gravitational force, but X component. X component of gravitational force, yani Fgx, it is restoring force because it is in the opposite direction of the displacement. Displacement is like this. Fgs, X in the opposite direction. And Fgx and displacement theta are directly proportional until 15 degrees. As theta increases, Fgx also increases. As theta increases, restoring force also increases. And magnitude of the restoring force is calculated by Fg times sine theta. This is Fg. This is F. So here, let's continue. Yeah. So as I said, it is rising from the zero level. As it rises, H increases. As H increases, gravitational potential energy increases. Then it's going down, gravitational potential energy decreases, but kinetic energy increases. At maximum displacement, here object stops, here pendulum's bob stops, which means their kinetic energy 0. So then according to, if you make a table, This is the equilibrium position, which is the zero level. So of course, at this position, gravitational potential energy is zero, but at maximum height, so at maximum displacement, which is the higher the pendulum's bob is at the maximum height, so from the equilibrium position, so then a pendulum's energy is entirely gravitational potential energy. Then it starts swinging back to the equilibrium position. As pendulum swings towards the equilibrium, its potential energy decreases, but kinetic energy increases. So, and at equilibrium position here, its gravitational potential energy is zero, but kinetic energy becomes maximum. And after it rises, it rising again. So it's rising, it's having the position. So the energy increases time, but gravitational energy increases. And here, then it goes to position at maximum displacement. So I'm split from equilibrium position to the other side. Pendulum's energy once again entirely gravitational potential energy. And first position, completely gravitational potential. Position, it's converted to completely, but position for both potential energy exist. But some of this energy, these two energies, always constant, which is known as mechanical energy. And in fact, this table is the same as simple harmonic motion, mass spring system, and gravity, simple pendulum. Only instead of elastic potential energy, we have here gravitational potential energy. Same, everything is the same. Directions are the same as the mass spring system. Magnitudes are the same. And this table is only changes what? Instead of elastic potential energy, we are going to write here gravitational potential energy. At maximum displacement, so because displacement is to the right, so restoring force is to the left. Here displacement is to the left, restoring force is to the right. When displacement is maximum, restoring force is maximum. When displacement is maximum, restoring force is maximum. Acceleration proportional to restoring force. Everything is the same. And gravitational potential energy. Maximum at maximum displacement because it rises the most. Maximum on the right side of the maximum displacement rises the most, maximum. Here it is zero level, so gravitational potential energy is zero. Kinetic energy is inversely changing with gravitational potential energy. Yes, if it is maximum, kinetic energy is zero because pendulum stops here. Kinetic energy here is zero because pendulum stops here. Velocity also proportional to kinetic energy, as kinetic energy is zero, which means velocity is zero. As kinetic energy is zero, which is velocity is zero. As kinetic energy is maximum in equilibrium position, velocity is also maximum in equilibrium position. So this table exactly the same for mass spring system and simple pendulum. Only changes, instead of elastic potential energy in mass spring system, here we have gravitational potential energy. And this is the graph how gravitational potential energy and kinetic energy changes. So right here, because object stops, kinetic energy is zero. This is kinetic energy graph. But it is at maximum displacement, potential energy, which is red, maximum. But as it's swinging towards equilibrium position, potential energy decreases, but kinetic energy increases. Look at here, potential energy red is decreasing, but kinetic energy blue is increasing. At equilibrium position, kinetic energy gets maximum value, so blue lines gets maximum value, but gravitational potential energy gets minimum value, so it's decreasing. And again, gravitational potential energy increases, as you see, increases, but kinetic energy decreases. This is the diagram which defines how kinetic energy and gravitational potential energy changing for a swinging pendulum. But some of these two energies are called total mechanical energy. If there is no air resistance or air friction are neglected, so then total mechanical energy of the system must stay constant. As you see, it's a straight line which is defining this energy is constant. And then we are going to define simple harmonic motion now. We are going to measure it. First one is we are going to define what amplitude is. Maximum displacement from equilibrium position is called amplitude. So max displacement is in simple pendulum is defined as an angle. So, but for a mass spring system defined as distance. So, and then positive A, positive theta maximum, negative A, negative theta maximum for simple pendulum. Positive A is positive x maximum, negative A is negative x maximum for mass spring system. but its maximum displacement from equilibrium position, which is definition of amplitude. And one cycle swinging from maximum displacement on one side of the equilibrium to maximum displacement on the other side, and then back again, is considered as one complete cycle. So you will start from maximum displacement on one side, go back to the maximum displacement on the other side, and back again. So this is defined in your book as one complete cycle or one cycle. As object is swinging one cycle, it travels a distance which is 4a. Why? From 0 to 1a, from 0 1a, from 0 to 1 more a, from negative to 1 more a, from 0 to a again a. So a, 2a, 3a, 4a distance are traveled in one cycle. But the displacement of the object is 0, so it goes back where it is, which means after one cycle, always travel distance is 4a, and object will turn back where it is, so its displacement absolutely indefinitely 0 after one cycle. And half cycle, this is half cycle. Half cycle is distance traveled is a plus a, which is 2a. But displacement can change. For example, here displacement is 2a, but sometimes object can start from point O, 1a, 2a, it can come back again to the 0. Yeah, and that's why we don't have a certain information about the displacement. It depends on where the object starts, but we can say that distance traveled by the mass on for half cycle always 2a. For quarter cycle, it is going to be a. Again, displacement can change, but distance is certainly a for a quarter cycle. And then we will define what period is. Period is the time it takes for one complete cycle of motion. So an object will start from positive displacement, maximum displacement from one side, go to the other side and back again. So it is time. This time is known as one period. So one period time, object travels a distance of 4a, yeah, a, 2a, 3a, 4a. In one period of time, object vibrates with a distance which is 4a. But half cycle, the time is, of course, will be half of the period. From positive or negative a, time is going to be half of the period or half period t over 2. For quarter cycle, of course, time is going to be t over 4. T over 4 plus t over 4 plus t over 4 plus t over 4. And if a 10th cycle takes 30 seconds, what is period of this motion? So we can calculate it very easily. There's an equation to calculate the period. Period is total time divided by number of cycles. Total time is 30 seconds. Number of cycles is 10. If we divide 30 by 10, which is 3 seconds. So period of this motion will be 3 seconds. Frequency is inverse of period. It is the number of complete cycles the mass swings through in a unit time in 1 second. This is called frequency. Its unit is negative second, negative 1 or 1 over second. Sometimes it's called hertz. For example, if 10 cycles take in 1 second, and there are 10 cycles in 1 second, then frequency of this vibration will be 10, because number of cycles in 1 second is the definition of frequency, which is 10. If 10 complete cycles take 5 seconds, what is frequency of this vibration? So again, we will use the equation, but inverse of period. Period was total time divided by number of cycles, but frequency is number of cycles divided by total time. Number of cycles is 10, total time is 5. 5, which is 2. For this vibration, frequency is 2 hertz. If one complete cycle takes 20 seconds, what is frequency? How many seconds? 1. In how many seconds? 20. 1 over 20 is the frequency of this vibration. As we said, frequency and period are inversely proportional. Period is themselves, for example, so the inverse of as power, which is equal to 1 over 5. And then we will find the period of Lambda equation for period, or Lambda equation for period of mass spring system. So L over G, root of L over G. And although field acceleration can affect period of so has effect on period, yes. Amplitude data, no. Mass object, no. But field acceleration, yes. This Q affects the period of pendulum. If you write so frequency is equal to 1 over 2 pi, you are going to flip this to 1 over 2 pi g over L. Frequency is 1 over 2 pi g over L, but period is 2 pi L over g. And calculate using this equation is not so hard, just mathematically you are going to use this. However, in your book, this is also explained how length, amplitude, mass, and free fall acceleration effects when they change, what changes. So this is also explained on your book. For example, if length increases, for example, if there are two pendulums at different lengths, but all others are the same, masses are equal, thetas are equal, and then g's are equal. If length increases, first pendulum travels a longer arc length than, shorter arc length than the second one. You see, delta S2 is longer than delta S1. And if you make a pendulum longer, arc length traveled by the pendulum increases. If arc length increases, which means time of travel increases, because if it is longer distance, you travel in a longer time. That's why pendulum's period is increases. That's why it's increasing. Yeah, as we said, period is changing with the length. This is one thing you should know about the length. Yeah, and if you increase the length of the pendulum, two things increases. One of them is the arc length. Second one is time of travel, which is period increases. And amplitude. If you make amplitude greater, there are two different pendulums at different amplitude they are swinging, but their lengths are equal, masses are equal, g's are equal. Arc length also increases. Look at here, this is small angle, smaller arc length. Greater amplitude, greater arc length. Your arc length also increases. But period does not change, because as you make theta greater, theta is greater, force also increases, acceleration also increases. That's why smaller arc length, smaller acceleration, greater arc length, greater acceleration. So effect, these two increasing effect cancels one another, and that's why period for this pendulum and that pendulum are equal. For that reason, we say that amplitude has no effect on the period, but of course it has effect on arc length. If you make the angle greater, arc length increases. If you make the amplitude greater, restoring force increases. If you make the angle greater, acceleration increases. But period stays the same. Period does not change. Mass. Equal, all others are equal, only mass will change. So pendulums have equal lengths and amplitude, but masses are different. Mass only determines the gravitational force changes here. Restoring force increases. However, acceleration is constant, because according to the second law of motion, acceleration force divided by mass. If you divide force by mass, so mg sine theta is the force, and divided by mass, look at that mass simplify. For that reason, acceleration is independent of mass. Yes, restoring force is great, and you increase the mass. However, acceleration doesn't change, because according to second law of motion, mass simplify. For that reason, arc lengths are the same for this one and that one. Their accelerations are the same, which means mass also has no effect on the period of the pendulum. Mass affects what? Don't forget, restoring force. If you use a greater mass at the same amplitude, so Fg sine theta, which is mg sine theta, restoring force of the greater. And free fall acceleration. Free fall acceleration has effect on the period, because greater free fall acceleration is greater restoring according to mg sine theta. Greater acceleration means greater acceleration according to g sine theta. If acceleration is greater, because they have the same length, for acceleration, they will period for greater acceleration. For that reason, yes, free fall acceleration has an effect on the period. T is, according to the equation also you can get it, T is equal to 2 pi root of L G. For mass spring system, we have only one equation, which is again mass of the vibrating object and K, spring constant determines the period of vibration. 2 pi m over k. Frequency equation 1 over 2 pi k over m. You are going to flip the equation. Mass has effect on the period, yes, but in simple pendulum, no. Amplitude has effect on the period of the mass spring system, no. Simple pendulum, also no. Spring constant has effect, yes. In pendulum, we don't have spring constant, yes. Spring constant k and mass has effect on the period on frequency of mass spring system. And briefly, I will explain how mass affects this spring period and the frequency. First, m. If you increase m, all others are kept constant. F is constant, A is constant, X is constant. According to the second law of motion, if m increases, because F is constant with kx, acceleration decreases, which means this object will start moving slower. So greater mass means slower motion. Slower motion means longer time of travel. For that reason, period increases. If mass increases, period also increases. And spring constant K. All others are kept constant. Say that K increases. If K increases, restoring force increases. Because M is constant, if restoring force increases, acceleration increases. Increasing acceleration means object will start vibrating faster. So then, yes, K also has effect on the period. So if you increase K, period decreases, but inverse effect. Amplitude. If amplitude increases, restoring force increases. Yes, restoring force increases. However, you also increase the distance. And amplitude means distance. Distance is increasing, restoring force increasing, acceleration is increasing. However, time of travel will not change. So making the amplitude longer increases the acceleration. However, you already made the distance longer. Time of travel will not change, which means period will not change for mass spring system. So this is all about section 2. There are some questions. Mathematical questions are not so hard. T is equal to root 2 pi root of L over G for simple pendulum. T is equal to 2 pi root of M over K for mass spring system. Period is inverse. You are going to flip them. So then you will make calculations in about the section 2. This is all about section 2. All right. So any questions? Sorularınız var mı? Peki. O zaman ben tamamlayacağım. I am going to finish this lesson. So at 1 o'clock, I will continue with section 3 and 4 of chapter 3.